So, hi everybody. Welcome to the After Café. Thanks a lot for sticking around. My name is Taylor Wood. I'm a graduate student in the material science department and a member of the McIntyre Research Group in astrophysics. And today I'm going to be talking about evaluating residual stress and strain states using X-ray diffraction techniques. So, just as an overview, I'll go over what strain and stress is briefly, how you can detect that using XRD, a couple of different techniques that have some advantages and disadvantages as far as geometry and XRD goes. And then finally, talk very briefly about synchrotron sources, which is another part of my research that I've done. So, thin film technologies, that's mostly what I'm working with. I will say that this XRD technique can also be used for bulk materials, but specifically, I work with thin films, particularly optical coatings, but thin films are extremely important in integrated circuits, wear-resistant coatings, and of course, optics. But cracking and delamination and bowing due to stresses is still a significant problem for their functionality. And measuring those stresses can often be difficult. It's important to make a little bit of a distinction when we're talking about stress and thin films between external stress and internal stress. For a standard bulk material, you might imagine a stress or an applied load over a large piece of metal or concrete or something like that. That would be an external stress distributed across a material. For thin films, because they're very small, we're looking more at internal stresses, which occur innately as a result of processing or structure. So these are going to be within the film because of deposition or adhesion or something else. So thin films are typically internal. They're often known as residual stresses as well. They're elastic in nature. Something kind of unique about them is they can exceed the yield stress of corresponding bulk materials. But they are hard to measure, especially with very thin films. Just in terms of the actual strain that is put on a material, strain describes how much of a material can deform relative to its original position. So commonly written just by length minus initial length divided by initial length. But for using X-ray diffractive techniques, we're then going to look at crystallographic planes, which is the same analog, except now you're looking at interplanar spacings rather than just a length distance. And what that kind of looks like is you may have an unstrained lattice parameter, which in this sense is cubic, under tension that may be stretched a certain way in the crystal planes, and under compression that may be pushed together in certain ways. And that's actually what we're measuring when we're doing XRD diffraction of residual stresses. We want to look at how much those interplanar spacings are changing based on what internal stresses they have. Um, Obviously, for single crystals, example I just showed was more for a single crystal, but most thin films are polycrystalline. And polycrystalline films are composed of grains that have many different orientations, like this one. So all of these blue, green, and pink planes are the same crystallographic planes, but they're turned in different orientations. And because they're turned in different orientations, they experience that internal stress within the film differently. So for XRD calculations, the way we calculate strain is by measuring interplanar spacings at a bunch of different orientations and then using the change in those spacings to calculate the overall strain state on the aggregate of this entire piece. So I often get asked, why use XRD to do this? It seems like it might be complicated. When there's curvature-based techniques like profilometry or interferometry that can sometimes be quicker and easier, and that is true. But there are some great benefits to using X-ray diffraction techniques to measure residual stresses. One being, it doesn't require a very specific thickness measurement. Obviously, it's important to have a clear thickness measurement of your film, but if that's difficult to measure for some reason, curvature-based techniques can be difficult because the calculation of that is highly dependent on the thickness. Second, resultant stress directions can be calculated. So you're not just getting an average stress, but you're also getting stress in certain different directions, like the 1-1 direction, or the 2-2, or the 1-3, or the 2-3 directions. So if you have a need to determine what the differences are between those, XRD can be a really great technique for that. Second, it provides calculation of triaxial stress states, which would be in directions normal to the surface. You can do depth profiling. Depth profiling is not something that's particularly easy with curvature-based techniques unless you physically remove part of the material and retake your measurements, but that would then be a destructive technique. Um, and finally, this is particularly important for our group. We work with making optical diffraction gratings. So we're making nanofabricated features. You can't really use profilometry or curvature techniques well on this because these have pattern, they have geometry to them. But because XRD is a highly geometry dependent technique, we're able to get information on those surfaces that we may not otherwise get. One obvious disadvantage to it is because you're detecting crystallographic planes, you don't have very great visibility to amorphous materials. So this is kind of how it works. Obviously, we're using Bragg's law to determine the interplanar spacing of crystal planes. This is would be a standard diffractometer, and I just want to go over a little bit of the motion for these because geometry is highly important to this technique. Um, of course, the source and the detector can move independently at different angles, commonly described as theta and 2 theta. But what's particularly important to this calculation and technique is also the rotational angle, which some might think of as yaw. That would be how your sample actually rotates around. And then also this tilt angle, which you can think of as pitch. And that's going to be how your sample is tilted with respect to the surface normal. And so when you're calculating stress and strain, you're going to use those interplanar spacings and all of those different orientations to look at the different grains in the crystal. And we're detecting strain. We can also detect stress by the generalized form of Hooke's law, and that's related to strain. The problem when you're making these measurements is that the strain is measured in lab coordinates, and stress is in sample coordinates because your sample has its own frame of reference as well. So these need to be aligned together using a tensor transformation. And this is a lot of figures and math, and I'll be happy to explain this more to people afterwards. But just for the purposes of this discussion, this is the way that these rotational angles and tilt angles correspond then to the strain and the stress. And you get this kind of long equation with a bunch of unknowns. You have 6 unknowns here, which means you'll need 6 independent rotational angles and tilt angles. And if you want to get a stress state out of this rather than strain, you can replace this with Hooke's law to get something that looks like this. Again, you have these directional stress states. There are 6 independent ones. For bulk material, I think all of these would be worth looking into, of course. For thin film materials, because the direction out of the plane is so small, we're typically going to refer to these as biaxial stress states, which means that these reduce down to just being 3 directions, one in the 1 direction and 2 direction and 1 2 direction. That would be in the plane of the actual film. And so what this looks like is basically just a linear equation from high school math or junior high math. And we can relate each one of these 3 directions of stress, sigma 1 1, sigma 1 2, and sigma 2 2, directly to the slope of our measurements. If we see a positive slope, we see a tensile stress. If we see a negative slope, we see a compressive stress. So this is, if we plot these strains or these interplanar spacing changes in the way that they change with orientation of tilt in our measurement, we can get a couple of different situations. In A here, this would be a truly biaxial stress, can be analyzed with a very basic theory that I just showed. If it's B, this is something called psi splitting. This would indicate a presence of an out-of-plane stress. So this is still calculable and you can still compute this, but you need additional information. So in addition to tilt angles in the positive direction, you will also then need tilt angles in the negative direction. And then by averaging those together, you can get that linear line. You can get a parabolic curve. That's going to indicate the presence of a stress gradient along the surface normal. Or you can see an oscillatory curve or seemingly no strong correlation, which would indicate that that particular stress state can't be analyzed using this technique. So how do you actually collect this data on the tools downstairs in the MCL? There are a couple different ways. The first is to just use Bragg-Brentano geometry. In this particular technique, we're going to use a fixed 2 theta range to look at one single peak and then repeat that measurement multiple times at different rotational angles, and at each rotational angle at multiple psi tilt angles. So this kind of looks like this. First, we would take measurements at the surface normal direction at 0-degree tilt. Then we would tilt the sample and repeat that same measurement at a different tilt, in this case, -18 degrees. And then we would repeat that and take the measurements again of D spacings at -35 degrees. So you have a data set that's begins to be pretty large as you take more, because you're taking maybe 6 or 7 tilt angles per each rotational plane. And you typically would take 3 rotational angles. So each data set is upwards of 18 to 20 independent Bragg peaks. In the MCL, I've been using the MRD to do this, and you can talk to Nicole more about getting trained on the MRD if you're interested in this technique. It has a Pixel 3D detector. It's a copper K alpha source. For residual stress measurements, it does have a variable spot size that you can change between 1 and 10 millimeters in both the X and the Y direction. Of course, the geometry of your experiment will determine the actual beam spread and spot size on the sample. It has a full 360-degree rotation of the wafer there, and also tilts from -90 to 90 degrees. It's very robust in terms of how you can move your samples. So if you're looking at orientation and all these different grains, this is a great tool to be able to put your sample in a very specific position to look at those different ranges. This is some example of data that I got from this. Again, this is one peak, and you can see that this is all the same crystallographic plane on the same sample, but taken at different tilt angles. And what you can see is that this 2 theta position is going to shift with tilt, and that's what we're tracking. So I looked at different samples of platinum, 50 nanometer thick, 35 nanometer thick, and 25 nanometer thick. All of these were evaporated samples that I did in the nanofab, and then I measured these using the MRD. And what you can see is you can begin to see a change in slope from this line. And remember, slope is directly related to the stress state. These are tensile stresses, which is common for evaporated films, so that made sense. And you can see that as the film thickness decreases, the slope also began to level out and the stress state reduced. When this was actually put through that formalism I showed before, and I extracted the slope and then used the equation I showed previously, you can then extract a single stress value in each direction. And so these are the stress values I extracted for 50 nanometer, 35 nanometer, 25 nanometer, and 15 nanometer films. And you can see that the trend that I found was as thickness decreases, there's roughly linear trend with how stress also decreases with that from an evaporated platinum film. I did not include data for sigma 1,2 on this, because sigma 1,1 in blue and sigma 2,2, those two directional in-plane stresses, are nearly identical in the films that I typically look at. And because of that, the shear stresses in sigma 1,2 are also very negligible. So there are some obvious benefits and limitations to doing it this way. One is you have good visibility to that positive and negative tilt angle. So if you remember, I mentioned that if you have triaxial stresses, you may need to look at both positive and negative tilts and then average them together. That's something you can do if you use Bragg-Brentano geometry. Second, depending on your geometry, of course, you have a much lower beam spread, because especially if you have a high incident angle, which can be a benefit if you're looking at a very specific part of your sample. One big disadvantage, especially for me, is this is very time intensive, because you're looking at maybe 18 or 20 different independent measurements to get one set of stress measurements. If you have very thin films like I have, and this is a bit of an intensity starved setup, then you have to take measurements for a very long time. So each of those short scans takes maybe an hour and a half. And if you're taking 18 of them, that adds up pretty quick. Of course, if you have a thicker sample or a bulk sample, that problem will not be nearly as acute for other situations. Again, as I mentioned, this can be intensity starved at very low thicknesses. This is neither an advantage nor a disadvantage, but just kind of a truth. Again, we're looking at single plane visibility for each set of measurements. So you're looking at the stress that's on the 111 plane or the 222 plane or the 220 plane, but not necessarily on all of them, unless you're taking independent data sets of measurements for each plane, which can become cumbersome very quickly. So you do have a better view of what that average stress is on a specified plane. And again, penetration depth is going to vary quite a bit also with incident angle. There is another setup you can do, though, that kind of fixes some of those problems, and that's grazing incidence XRD. So especially for thin films, grazing incidence is going to be a big benefit because you get a significant signal boost. And the way this kind of works is rather than looking at one plane multiple times at different sample orientations, now you're going to fix the sample and the source incident angle, and you're going to look at multiple planes and compare how they are changing based on what they should be for an unstrained lattice parameter. So you still need those same angles, rotations, and side tilts, but the side tilts this time are sort of pseudo side tilts that are determined by the angle of incidence, which is set at the beginning, and the theta angle, the Bragg angle. So in the MCL, you can use the Empyrean to do this. It has a copper K alpha source. One really great thing about using this tool is that it does have specialized optics for grazing incidence XRD, has parabolic mirrors and other solar slits and things that you can put in to really get a nice signal from that. There's also a translational stage, which will allow you to tilt your sample and move it in X and Y and Z. It has a manual rotation on it, so you can track that as well. And if you look, you can see from this picture on the right, it's pretty robust in terms of how far it can turn in 2 theta. So I've taken this all the way pretty much to the max on this side, and it's a sight to see. So this is an example of the scan data you get. One benefit also to grazing incidence data is it's very clean. You don't get any substrate peaks in because substrate peaks are going to not show up for this geometry if you're using a very single crystal substrate like silicon. And I was able to measure 8 different peaks and then use that to create this linear line I'm looking for. In this case, we're plotting strain rather than interplanar spacing, but it's related to that same idea versus sine square psi. So this is, again, a 50 nanometer platinum evaporated film. Again, you see that it's tensile. But in this case, each one of these points represents the measurement from a different crystallographic plane. The fitted slope that I got yielded a stress in the sigma 1,1 direction of about a gigapascal. Just as a note, this was the Bragg-Brentano result from the same sample. It was about 800. It's not a direct comparison necessarily, because if you recall, this is only for one plane, the 111, and this is a more holistic view of the stress on the entire aggregate based on all of those planes. But they do show very similar trends. Some benefits to this, and as far as calculation, the calculation is the same, but first of all, it's much, much faster. Rather than 20 hours, it takes 1, which is great. You have improved thin film signal significantly. Another pretty cool thing is you have a consistent penetration depth, and that penetration depth is highly dependent on this alpha angle of incidence. So what you can do is take repeat measurements maybe 3 or 4 times at different incident angles, and you'll have a continuous, relatively consistent penetration depth for each of those. So you can look at how stress changes with penetration depths based on that. So if you have a sample that's maybe a micron thick and you want to see what it looks like at different levels, maybe at the surface, 750 nanometers, 500 nanometers, 250 nanometers, you can do that if you set your source correctly. One disadvantage is that because of the way the diffractometers are set up, you don't get that same visibility to positive side tilts. And the reason for that is because if you were to go the other direction, I guess, take this down, then your sample would block the detector. So it's just geometrically not really possible. Another big disadvantage, depending on what you're doing, I suppose, is you have really significant beam spread. Because this incident angle is only 1 degree, you're going to get a beam spread that's really enormous and could go across your entire sample. So for mine, I set mine at 2 degrees when I was doing some work at the synchrotron, and the spot size was a half a micron, excuse me. And because of this 2-degree incident angle, it spread the beam to be 15 millimeters long. So it's quite significant. And again, you get visibility to multiple planes per measurement scan. And I put this in blue because this is not necessarily an advantage or disadvantage, but something that you should be aware of. So so all of these techniques that I've described so far are available and are very robust in the MCL downstairs. And Nicole and Anthony can train you how to do those. And it's worth looking into for sure if you're interested in looking at residual stresses. For me, because my films were particularly thin, I did have a need for a little bit more flex. So I went to look at the synchrotron, but I want to just point out that this is not necessarily the best road for everybody. Um, these are robust tools in the basement, and they're definitely worth using. And you should go to a synchrotron source if it's necessary. But I did go to a synchrotron. Again, the benefit here was that it was a very high flux, so the thin film signal was, of course, better. Very, very fast scan time. I could take infinitely more data in just a few hours than I ever could have here. So if you have a need for taking multiple points around your sample or multiple angles, this really made that possible. It has a much smaller spot size and variable energy. So another way to do depth profiling of residual stresses is if you use different energies, because they will penetrate more deeply into your sample. So that's something you can do too if grazing incidence doesn't work for some reason. Some big disadvantages of this, though, of course, is that beam times are restrictive. They're far away from where we are. They can be difficult to get time on. You need to write a proposal. And just from experience, I'll tell you that's not, it takes some time to build a relationship with beamline scientists. If you're interested in doing that, I would recommend reaching out to them, explaining what you want to do. I would also definitely use the lab source GIXRD tools here first so that you have a proof of concept of your experiment. That's an important part. And then they can also be more restrictive in sample motion. So I mentioned that the MRD downstairs is very robust in how it can move. Because beamlines are quite large and have a lot of different parts to them, stage crashes can be really problematic. So there's a lot of restrictions on how far you can move things. Like the tilt range was almost half of what I could move here. So definitely, just to underscore that, perform your experiments on lab source diffractometers first. But you can see that the signal to noise ratio is much better. These are the same samples. This was measured on a lab source, and this was 50 nanometers. And as you get lower and lower in thickness, that signal to noise ratio becomes higher. And that kind of was really helped a lot with the synchrotron. This was interesting as well, where I saw these kind of level out on lab source because they were getting so low in thickness. We saw a really clear trend with thickness of film and stress, such that even an evaporated film at a certain thickness at this condition, you could see a transition point where it moved to compressive stress, which was really an interesting thing to see. And again, because I was able to take more data, we started to do mapping of stresses around the sample. So XRD is a really robust technique, and it's non-destructive. So it's a great way to look at residual stresses for your samples. For bulk materials and for thin films, the basic technique is the same. You can get directional stress states, which you can't really get so well in curvature methods. You can get stress depth profiling. It's measurable on a lot of different types of surfaces, including patterns, if you orient your sample correctly. And you can map across a sample in a more specific way sometimes. And Bragg-Brentano techniques and grazing incidence techniques that I talked about, they have their own advantages and disadvantages, but both are capable to do downstairs. And we have all of the tools to do them and have worked them out. There is specialized optics for them and also software to help calculate the residual stress changes. The thing that can be kind of complicated in all of this sometimes is seeing what you're actually measuring and then coordinating that over to the residual stress. And I think that the software that they have down there can help you do that. So just want to thank, of course, my group, and my research is funded by NASA and the scientists at Chess for all of their help, and of course the GIXRD staff members in the MCL. And thanks very much.
So feel free to ask some questions.
So I missed the beginning of your talk, and I apologize for that. But what's the uh, largest sample you can put in terms of like height? And I'm thinking like a polishing sample. If we were to get ready for like EBSD, is it possible to put this in to try to look at like residual stresses before they go over there?
Yeah, I mean, I think that the size of the sample is going to be entirely dependent on the diffractometer. For example, like the synchrotron one at Chess could take a sample that was pretty large because the sample stage could drop down and up. I don't know what the exact limit is for the diffractometers here, but Nicole and Anthony might.
So for grazing incidence, we have about 25 millimeters, and the X dimension is, so again, for grazing incidence, in most cases on our instrument, you're probably going to irradiate the entire surface of the sample in the direction of the beam. And we can control what we call the axial direction by masking it to the sample size. So that would probably be the best for what you're thinking, especially because the sine squared psi technique would take a very long time, 20 plus hours probably to get that information. So yeah.
Yeah, thanks, Taylor. When you go to the beamline and they're using higher energies, how deep can they actually probe? Once you have access to a synchrotron, because we're pretty limited to close to the surface in the lab source. But how deep can they go at the synchrotron?
So obviously it depends on the energy. The beamline that I used at Chess went up to 16 keV. So you could, and also it depends on the angle of incidence as well. But if you're looking, especially at higher order peaks, like up at higher 2 theta angles, then you could penetrate fairly deeply. So you're right, like it's kind of a surface level technique, especially if you're doing grazing incidence here, and it won't penetrate very deeply. I'm not sure that I have the number in mind, but I do know that at the beamline, because they've done experiments like this in the past, and I have spoken with them about it, they will change the energy from I think 8 or 7 keV to 10 keV to 16 keV. And one thing they did note was that there is a bit of an overlap between those bands that are being irradiated. And so taking into account that you're also receiving signal from some of the other depths is something that they do have to tackle. I think with the grazing incidence technique, if you choose your incident angle correctly, then that penetration depth is fairly constant across that entire 2 theta range. And I think you and I looked at that plot before that showed a pretty leveled out penetration depth. So I think that would be a more clear way to make sure that most of your signal is coming from different depths.